This doesn't look right. Okay, how do I switch it around? Hi, everyone. Clearly, the camera is pointed away from me at my closet. And I'm trying to find how to fix that. To be honest, I don't know yet. Don't bother. I have 6 lovely viewers who are watching my closet. Well, criminy. You'd think this would be so simple, but it's not. Ah, okay. Had a all right. I'm a little late. I'm sorry. I'm getting my textbook to the Redox page. I still haven't checked that question yet, but I checked the other ones. So, okay. It's on the way then. Okay. I think this will work fine. Okay. Let's look at the questions. I guess we are starting with equilibrium. It's a tough topic right at the beginning, but let's go for it. You can see that I have a lot of questions here, so I'm going to kind of roll through this pretty fast. Thank you to the, for putting in the parts. Okay. I put my other thing. Okay. Okay, here we go. So we'll start with what's the definition of KSPQ, KEQ. Oh, I'm going to do a real timer, but I don't have my phone in front of me, so we're just going to go with the old way. We're starting 9:18 is when I'm starting this one. Okay, what's the definition or difference of KSPQ and KEQ? They're really kind of all the same. Anything with a K, you kind of do it the same method where you do the products or the reactants. Anything with Q is the same idea, products or reactants. The only difference with Q is you're questioning, are you really at equilibrium or are you not? The K symbolizes that, yes, you're at equilibrium, and the Q says, I wonder if I'm at equilibrium, but really you calculate it all in the same way. So that's kind of like the biggest difference between KSPQ and KEQ. KSP specifically looks at the solubility product constant of any kind of salt. So KSP is when you look at the solubility of something. Q is what you use when you're questioning, am I really at equilibrium? Lots of times it's with QSP, is it in equilibrium with solubility? And then KEQ is just playing equilibrium of any equation, not specifically solubility, but any equation at all. Okay, so moving on to number 2. That was from the worksheet. Yeah, number 4 on the worksheet. So that goes with this question down here. all the same. So we'll start this at 920. So I'll show you how I did the equation, and then I'll go to this part I that's in there and try to help you out there. Okay, let's make sure I can share my screen. Okay. Okay. Oh no, where did I put this? I'm on like Microsoft 10 and I don't know where to find my, I just did it. Now where do I find Paint? I know, I'll ask Cortana. Ah, perfect. All right. Okay, so we're doing number 4 on the KEQ part. My video is keeping up. Okay, excellent. Okay. What is the concentration of silver ions in 1 liter of a saturated solution of silver carbonate? So first thing I would do is write down what silver carbonate is. Silver is a +1 and carbonate is a 2-. That gives me Ag2CO3. There's silver carbonate, and I'll have to write the KSP for that. The KSP for that is just its ions. In the brackets mean molarity. Silver, 1+ is the ion, and carbonate, 2- is the cation, or the anion. Cation is 1+, anion is 2-. And there happens to be 2 silver, so I want to put a little 2 up top here. It's squared, the molarity is squared. Okay, so now at this point it says, what is the concentration of silver ions in a 1 liter saturated solution? The volume really doesn't matter because it's always going to be saturated. So whether you have 2 liters, 10 liters, or 1 liter, you're still going to be a saturated solution. So that 1 liter part really doesn't matter to you at all. What does matter is the only number they give you being the 8.1 times 10 to the -12th is what KSP is equal to. So that one matters. And then if I think about my Ag2CO3, when I put it into a bucket, it will make silver ions and carbonate ions, specifically 2 silver ions. So let's say I put in X amount of silver carbonate, then I will get 2X of silver ions and carbonate ions. For every 1 of these I put in, I get 2 silvers out and 1 carbonate out. That's why I put in the parentheses 2X squared and the X. There are 2 silver ions, so that's why it's 2X, and there's 1 carbonate, that's why it's X. Now you might be thinking, well, what's up with this 2? Why do we have this 2 and this 2? I mean, aren't you using the 2s? They're 2s for different reasons. This 2 down here, this bottom one, is because of the reason I wrote down here. X makes 2X. For every 1 of these I put in, I get 2 of these out. This upper X up here is by definition. It's how we define KSP. KSP is defined as having a squared up here. It's how all the math worked out, how the chem gods figured it out. So that 2 is by definition. And the red 2, the little 2, this red 2 down here is by the X2X factor. Okay, now I'm going to keep doing my math. So now I'm going to simplify. 8.1 times 10 to the -12 is equal to 2X squared is 4X squared times X, which is equal to 4X cubed. So then I'm going to divide both sides by 4 and do the cube root, and I get that X equals 0.000125. Sig figs in these problems don't really matter because the KSP is the only number we're dealing with, and that's infinite sig figs. Whatever sig figs you do sounds good to me. Now that's not the answer though. The answer comes into, the question actually says, what's the concentration of silver ions? So what the answer is asking for is, what is this bracket thing? I have to do a different color. So it's asking, what is this? Which means, what's the silver ion concentration? Well, that bracket thing is equal to 2X. That's what I said right here. And I know that X is equal to this. So my end answer is 2 times my X value. 2 times my X value gets me 2.5 times 10 to the -4. And that's how I got my answer that's on the worksheet. Units, the brackets mean molarity, so molarity it is. That's how I do that problem. Now, there was another question. says, when solving questions like this in the KSP expression, sometimes concentrations are squared because there's a coefficient. But when setting up the ICE table, sometimes we put 2x and other times we put in 2x squared to solve this. Okay, so I hope that I also solved this person's problem by the 2x versus the 2x squared part. Yes. I think I did. I'm going to do another ICE table problem that looks like down here later on. So I'm having the worst of luck today. I think it's picked up again. I put my screen back together and my computer just completely shut down. I have it plugged in. It's charged. I don't know what happened. I hope my thing's picked back up. Okay, good. All right, I'm gonna go back and look at my screen. This should pick up. Okay. I think I'm looking at number 2 on our Google Doc, and I think I solved everything for number 2 in the equilibrium. If I didn't, to that person who's watching, please let me know. For 1B on the review worksheet of equilibrium. Okay. I feel my luck is going to be awful today with this computer system. To all you lovely people who are watching, I'm sorry. I hope you got, pie with you or something. Okay, I'm going to talk about 1B on the review worksheet. Shouldn't be no change as only pressure changes as a result of changes in volume make a difference on equilibrium position. Yes, volume does make a difference, but we can see here with 1B a decrease in pressure. If they say a decrease in pressure, the only way to change pressure is to change volume. So you kind of have to assume the volume has changed. So, I hope that this is picking me up. I go to so if we do the problem that we've got, 2N2O5, that's a gas, makes 4NO2 plus O2. Okay, it's working. And those are both gases. So on this side, I have to count the number of gases I have. I have 2 moles of gas on this side. On the product side, they're all gases, so I have 5 moles of gas. So if I change the pressure, and in this part it says I'm decreasing in pressure. If you decrease in pressure, that's pretty much equal to increasing in volume. We learned that Boyle's law is an inverse relationship. If you increase the volume, then it has less pressure. There's less times it's going to hit the sides. So if I have a bigger volume, well, then I've got lots of space. I want to keep lots of people in that room, and that's why it'll shift to the right. It's got so much space, it'll hit each other less often, and it'll create this 5 moles side. There's more room, more space. I like to think about more room, more space, have more people. In this case, it's moles of gas, so we'll shift it to the side where there's more moles of gas. So it will go to the right. I just 29. Okay, so QSP is my next one. How do you do it? And if you guys have a question for me as you're watching the video, like put it in red on this screen so I can really see it. Otherwise, there's so much writing I may miss it. Okay, QSP, how do you do it? Can you go over how to see if a precipitate will form when comparing a QSP value? Yes. Can you go over it? And then common eye effect. Okay. I believe I'm still on the screen right here. Yes. Okay. Yep. All right. So I can make up a problem of QSP. Silver carbonate's a good one, right? Okay, let's do that silver carbonate again. Ag2CO3, 8.1 times 10 to the negative 12 is our KSP. Okay, let's say you've got silver nitrate, and you're going to add to it sodium carbonate. If you do that, it does form a precipitate of silver carbonate, but only if you've got enough ions to make that happen. And it'll also make sodium nitrate. Balance the equation here. Okay, so let's say in this problem, I'm totally just making it up. Let's say we put in 0.001 milliliters, because we put in 1 drop of that, and it has a concentration of 0.05 molar, which is totally the concentration that we used in the lab. Would I expect you to do this on the theory part? No, probably don't calculate it. Okay, so then, and sodium nitrate, let's say I've got that at 0.002 molar, and you have 10 milliliters of it. That sounds good. Let's say you mix these two up and you want to know, would I actually make a precipitate? My precipitate in this case would be my solid or my sodium carbonate. Now it has a really, really low KSP, which means it pretty easily would want to make a precipitate. But to know for sure, you've got to calculate it. So we would calculate the QSP because we're questioning, would I really make silver nitrate? I'll write the QSP just like I would do in a KSP, silver ions squared, because there happens to be 2 of them, and my carbonate ions is a 2 minus. And then I'm going to start calculating my QSP. I'm going to do these big brackets here, squared. Okay, so I want to basically calculate, well, what's the molarity of silver ions I have, and what's the molarity of my carbonate ions? I don't know how Han really did these problems, but this is how I do it. So my molarity of my silver ions is going to be moles of my silver ions per liter of total solution. My total solution happens to be 0.001 mils and 10 mils. So in liters, that is, if I take my 0.001 milliliters, that'd be 0.000001. That's it converted to liters, because I got a 1, 2, 3, move it over 3 to the left, plus my 10 milliliters, 1, 2, 3, 0.01 liters. That's my total volume. 1, 2, 3, 4, 5, plus, which is the same as my total liters from my carbonate over here. My carbonate, I need to get moles of carbonate ion per total volume. My total volume is the same in both cases. Okay, so let's go over to my silver ion part again. I happen to have 0.05 molar, or moles per liter of my silver ions. I need to multiply it by the amount of silver ions I put in. In this case, I did 0.001 milliliters, or if I put that in liters, it's 0.000001 liters. That way they'll cancel. And then I need to This is 0.05 moles of silver nitrate. I need to convert my 1 mole of silver nitrate. Silver nitrate will have 1 mole of silver. Now you might be thinking, 1 mole of silver nitrate, 1 mole of silver. Why did you even do that kind of fraction? Well, this fraction right here could be important in like my sodium carbonate. For every 1 of these sodium carbonates, I get 2 sodiums. So then it wouldn't be a 1-to-1 ratio, it would be a 1 on the bottom and the 2 on top. So that's when that case when it really matter. So let's go over to my carbonate one over here and see if it's going to matter. Okay, I'm trying to get the moles of carbonate on top. So I'm going to start with what I got in my carbonate. I have 0.002 molar, or 0.02 moles per 1 liter by definition of sodium carbonate. That's what this 0.002 big M means, 0.002 moles per 1 liter. I'm going to multiply it by how many liters I have. I happen to have 0.01 liters. I put the 10 milliliters into liters. And then I'm going to multiply it. Got to get rid of this moles of sodium carbonate. So I'll do 1 mole of Na2CO3 happens to have 1 mole of carbonate. So once again, it's a 1-to-1 ratio. So we got lucky there. I'm now busting out my calculator. Just going to push all these buttons in. So I'll start with my silver ion one. 0.05. Is it raining? I have windows open. It is not raining. It was the dogs. Okay. All right, I'm still pushing buttons. This part down here is. Okay. Okay. I'm going to erase this so I can write down here. So this part of my, oops, calculator, I got 0.000005. I'll have to square that times in this parenthesis I got 0.00199998. Okay. Take those, multiply those together. I got equals 4.99. I'm going to just go sig fig to 5 times 10 to the negative 14. Okay, so that's my end number. Are there units on this? No, because KSP, QSP doesn't have any units. That's my end answer. So that's a really, really freakishly small number. That means there are really, really few ions in solution. All this math that I did calculate how many ions I have in solution. I have very few ions in solution. But according to my KSP, I don't need many ions in solution. So I asked myself, do I happen to have enough ions? 10 to the negative 14 is really small, and it's smaller than my KSP. If your QSP is smaller than your KSP, you do not make a solid. You don't have enough ions in solution to make a solid. They won't find each other and hook up. If your QSP is greater than your KSP, then yes, you do make a solid. And if your QSP happens to equal your KSP, then yes, you will have made a solid because it'll be a saturated solution. Well, QSP equals, I guess it's exactly equal. It's saturated and has a perfect amount, so no, you're not going to make a solid. Oh, okay, there you go. That's a highly complex problem, wouldn't you say? I'm scared to put my screen back in. It might go out on me again. I hope it doesn't. Okay, it didn't. That's awesome. Okay. Okay. Here we go. Can you go over the common ion effect? How do you know pH is simply known Ka-NH? Okay, can you go over the chem and ion effect question? Sure, we'll make one of those up. Here we go. Okay, I guess we should stick with silver carbonate, right? It seems to be a common, good enough one to me. Silver carbonate 8.1 times 10 to the negative 12 is its KSP. Okay, so let's say we have a saturated solution of silver carbonate, and you are going to add sodium carbonate to it. You happen to add sodium carbonate to it, and you're going to add 0.1 molar. The question would be, how many silver ions? Yep, how much silver ions do you happen to have now? Okay. So let's start by writing my KSP equals silver ions squared again and carbonate. So there's my KSP equation. I like to also write my equation. Once again, I'm not exactly sure how Han did this, but I know that she used an ICE table. I think she called it a rice table. The R being the reaction, I think. And there's two of those plus carbonate. Okay, ICE. Now this part here, my left side, my silver carbonate is a solid, so I don't really have to care about that at all. I don't have to fill in numbers there because it's not even found in my KSPs. We know that solids aren't found in the KSPs because their concentrations don't change. Only the molarity in gases, molarity of gases and aqueous things change. So that's why they're the only ones in the solution. Okay, so initially I've got 2x and x amount of these solutions. Now what I'm doing in this problem, I'm saying is you have a saturated solution. That's my initial. I say you have a saturated solution. And then you change it, and I'm saying you added 0.1 molar of Na2CO3. Well, the Na part really doesn't matter to us because it's not part of my KSP equation, but the carbonate does. So for every 1 mole of Na2CO3 I put in, I get 1 mole carbonate out, which means I've added 0.1 molar of this. I didn't add any silver, so I don't have to write anything there. And now I'm going to add up the two parts. I'm going to say 2x. 2x plus nothing equals 2x. And then x plus 0.1 molar, I don't really need the molar here, is my second part. Okay, so now I'm going to put this equilibrium part into my KSP, because KSP means at equilibrium, so that's where I want to put my numbers. So here I'm writing my KSP again, 8.1 times 10 to the negative 12 equals 2x, 2x is my silver, 2x squared, times my carbonate, happens to be this down here, x plus 0.1. Now in this case, it's going to turn into a quadratic equation, and the chem gods hate quadratic equations, so they would never want to do that. The only time you're going to do that is in AP Chem, and this is not AP Chem, so I'm not going to expect you to do that. What you are going to have to know is that if we look at this part here, this is the part that's making it a quadratic equation, so we consider that to be kind of evil. So we have to say to ourselves, we have x and we have 0.1. Which one is bigger? Well, my x is dependent on my KSP, and my KSP is super, super small, which means very, very few ions are actually dissolved inside here. So my x is freakishly small. This is much, much less than, those are my less than signs, 0.1. It is so much less than 0.1 that we say sig fig wise, it doesn't even matter. So that's how we can say that x plus 0.1 is really just equal to 0.1. 0.1 is what I'm changing this to. Now when I simplify it, I get 4x squared times 0.1. Okay, so I get 0.4x squared is equal to 8.1 times 10 to the negative 12. I'm kind of running out of space here, sorry guys. So I'm going to simplify and solve for x. So I'm going to take 8.1 10 to the negative 12, divide that by 0.4, and take the square root of that. I get x to equal 4.5 times 10 to the 10 to the negative 6 molar. Okay, back to my original question. My original question said, what is the concentration of silver ions when you add 0.1 molar of carbonate? When you add 0.1 molar of carbonate, the reaction shifts. This side gets too heavy, so that according to Le Chatelier's principle, if this side is too heavy, it has to shift to the left, shift to the left to make more solid, and since it makes more solid, you're going to lose some of this concentration. So the question is really asking how much do you actually have left? Well, I have X, 4.5 to the 10 to the negative 6, but I need to find the concentration, and I called the concentration 2X. So therefore, my concentration is really going to be 2 times this X, or in other words, 9? Yep. 9 times 10 to the negative 6 molar. And that's my end solution. Okay. Wait, you don't have to see my lovely face. Let's go to the screen. Oh, I forgot what time I started at. Oops. I'm broke. 9.5. Okay, acid base. Is MdOH2 a strong base, or is it an exception for the G2 hydroxides? Strong and weak bases. I wish I had my periodic table with me. There we go. You have a strong base when you have anything from the first or second group, and that is hooked up to an OH. The only exception for that is beryllium. So, so magnesium hydroxide is a strong base. Are there any other exceptions? The only one who is not a strong base from group 1 and 2 is beryllium oxide, hydroxide. Scratch that. Beryllium hydroxide, BeOH2, is our only exception for a strong base. It's actually a weak base. Okay. That one was at like 946. When I use the formula, this mainly affects question 15 in the review worksheet. Yeah, it totally does. Since magnesium chlorite right there, both of them are the conjugates of strong acids and strong bases, that's why it's a neutral solution. Okay, moving on to the next question of acid base. When I use the formula you gave to calculate number 11 on the chapter 18, yes. So I actually called Han about this to make sure I understood how she taught it. So I'm going to show you how I would teach it and how she would teach it, and then we should be good. Okay. Okay, so for this problem, it's sodium hydroxide is reacting with sulfuric acid. Double replacement reaction, I will make water and sodium sulfate. Balance the equation by putting 2 Z's in. So it says in the problem, I want to know the molarity of this sodium hydroxide if I happen to use 38 milliliters of the solution. And it's titrated to an endpoint of 14 milliliters of sulfuric acid, which is 0.75 molar. Okay, I'm going to do it the Han way. So the Han way is MAVAA equals MBVBB. This is the Han equation, and I did call her up, so that'll be on, I'm just going to write it on the blackboard tomorrow so that you can know it. This really affects especially 6th hour, because I remember talking to a couple groups about this equation. I didn't know what she was teaching you. Anyway, beside the point. So here's my parentheses I'm going to fill in. Okay. MA stands for molarity of the acid. This is clearly my acid, my sulfuric acid. So my molarity is 0.75. My volume is 14 mils. It doesn't matter if it's in milliliters or liters, since you have milliliters on both sides, it'll cancel out. So it's totally cool. Units, as long as they're the same on the left and the right, you're good. And this A stands for how many hydrogens you have. There happens to be 2 hydrogens, so I'll put a big 2 there. Molarity of the base, that's what I want to find. VB is a molar volume of the base, 38 mils. Once again, milliliters, so we're good. And then the B stands for how many OH groups you have. That would be 2 in this case. Oh, I'm sorry, 1. So this might be why things are getting a little funny for you, because in the Han way, you don't actually need a balanced equation. So you really have you're just counting the number of H's and OH's in the compound. When you do that and you actually calculate the buttons, I'm going to do it again, even though I did it earlier, because I was worried that I might screw this up. You get 0.55, which is the answer. Yeah. BB equals 0.55 molar. Now, if you're going to do it my way, you don't have to. but I'll show you what my way is. My way MAVAB equals MBVBA. And that's what you see in the equation sheet. Ettinger's is very similar to that. So if you use my way, the numbers are very similar. MA is still 0.75, VA is still 14, MB is still what we want to find, and 38 is still VB. The only difference is the B and the A. This B stands for the coefficient of the base. That's when we go back here to this 2. Here's the base. The coefficient in front of it in the balanced equation is 2. 2. This A part over here is find the coefficient in front of the acid. There's no number in front of the acid, which means it's a 1. A 1. You can see I'm using all the same numbers. It's just how I'm defining things that are a little bit different. So either way I go, I'm still getting the 0.55 molar. Works out for that person. Okay. I'm really bad at times today. We're number 11 on how to do the steps. I just did it. 12 and 13 in the same review section. I'm not going to do number 12 for you because I just did one just like it. So I'm going to let you try it your way to that person. I will do number 13 though for you. Okay, so a buffer solution is prepared by mixing equal quantities of formic acid, HCHO2, and sodium formate. Write the equation that shows what happens when first acid, then base is added to this buffer. Okay. Okay, so when you add an acid, what you're really adding is H+. Now buffers work because they soak up the H pluses or soak up the OH minuses that you put in there. They keep the pH from changing. The only thing that changes the pH is adding H pluses or OH minuses. So as long as you soak them up or cancel them out, then they really can't make an effect. So my bases are the OHs, my acids are the H pluses. So basically what I have to do is find somebody to react with them. This is my simplistic version. If I really taught this in class, it would be a lot more complex, but I'm just going simplistic. So if you look at our buffer, it's this guy on the left plus this guy on the right. Those two together will make the buffer. So if I had to, the next questions I'm going to ask you is you can only answer acid or base. That's it. This one on the left, is it an acid or base? You'd have to say acid. This one on the right, is it an acid or base? You'd have to say base because it doesn't have an H out front. So that's exactly what you're going to do. If you have an acid and a base, they're going to react with each other and neutralize. So let's look at my acid. I'm going to take my acid, my H+, that's what I'm adding in the bucket, and I'm going to have to react it with a base. Who's the base in the bucket? This guy, NaCHO2. And when you do that, the H+ takes the place of the Na, so the Na is just flying around by itself, and my HCHO2 is now hooked up together. Well, this is an acid. Wouldn't the H come off? No, this is a weak acid. And weak acids, the H's stay on. So here, my H has just been soaked up. It's been hooked up with this guy, so it can no longer float around. If it's no longer floating around, the pH can't change. Okay, in my other part, I have my base, my OH minus. If you are a base and OH minus, who would you want to hook up with? The acid or the base? Totally the acid. Boop. HCHO2. And if these guys react, well, now the OH is going to be attracted to somebody, this H+, and they'll make HOH or water. And then CHO2 will be floating around, 1 minus. Now, if you look at those things that we made water, neutral, and CHO2, also a semi-neutral thing. I know it could hydrolyze and stuff, but pretty neutral. So now we're looking at two things that are neutral when OH minus was before, which was clearly a base. So now that you have water and this guy floating around, the pH can't change because there's not H pluses or OH minuses floating around to change the pH. There you go. I'm starting to go faster. I've got a lot of questions here. Oh boy. Okay, to the next one. Could you go over how buffers work and go over an example? Totally just did. How do you know if something is a strong base or acid or weak? The strong acids are ones you just have to memorize. I think there are 6, 8. I don't know exactly. They should be in your notes. They're sulfuric, nitric, hydrochloric, chloric acid, not phosphoric, hydrobromic, hydroiodic. 6. Sounds about right. 6. And the strong bases are the ones that are in group 1 or 2, all except, so anything from group 1 and 2 that are in the periodic table hooked up with hydroxide will be a strong base, except for beryllium. Beryllium hooked up to hydroxide is not a strong base. It is a weak base. Everything else that I've listed would have to be a weak base. How do you find the pH of something knowing the Ka and H plus of concentration? I'm taking this one. I think there's something, oh yeah. How do you find the pH of something knowing the Ka and H plus concentration of it? Okay. So it seems to me like if you know the H plus of something, then you could calculate the pH, just do the negative log. But I don't think that's what this problem is going at. This person is going, if you have an acid, what would be the pH of it? I think you're looking for like a more complex problem. So let's say you know the Ka things. Okay. I gotta look up some Ka values, it looks like. I think there's a table in the back of your textbook of Kas. In like one of the appendices. Let's just look at Ks. Okay. All right, I'm on page, oop, that doesn't have any Ks. Here we go. Page 647 in your textbook has Ka values, and that's why I'm heading there. We'll do hydrocyanic acid, because that sounds like a good one. (6.2 10 to -10) is my Ka. Okay, so yeah, we'll go with this problem. Let's say you put in hydrocyanic acid and you have a 0.1 molar solution. What is the pH of that solution? There. I think that would be a problem that this person is trying to get at. What is the pH of a 0.1 molar hydrocyanic solution? You would want to create an ice table or a rice table where I put in 0.1 molar of this hydrocyanic acid, and initially I don't have any of it because it hasn't equilibrated yet, hasn't gone through equilibrium. So my 0.1 minus X, because some of this has now broken apart to create X amounts of H and Cn. So that in equilibrium, 0.1 minus X equals, will produce X amount of H's and X amount of Cn minuses. Now in this case, you're never going to have a 2X because acids always come off one hydrogen at a time. So you're never going to have a 2X in any kind of Ka table. So now if I write my Ka, products over reactants, I'll have my H plus and my Cn1 minus over my reactants, HCN. I'm going to put in my values that I've got. Ka 6.2 times 10 to the -10 equals, on the bottom I've got my HCN, which is 0.1 minus X. On the top I've got X amounts of both the H and the Cn1 minus. Now this is once again going to lead to a quadratic equation, which the chem gods hate. So we do everything we can to try and get rid of it. That's why we look at 0.1 versus X. And we say to ourselves, okay, the Ka is 10 to the -10, which means very little of the H pluses will come off, which means my X value is very, very small, much smaller than 0.1. And I know that because very little of the reaction is going to go to the right. That 10 to the -10 means most of it is going to stay to the left because it's a weak acid. Okay, so if 0.1 is greater than X, I can really just say this bottom part is 0.1. If I simplify, then I've got X squared over 0.1 is equal to the 6.2 times 10 to the -10, which means if I use my lovely calculator, I can solve for X. I got x to equal 7.9 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the negative 6 molar. Good. Now my x is equal to my H plus and my Cn minus. Now the whole problem that I'm trying to do is solve for pH. So my x is equal to my H plus concentration, and if I have the H plus concentration, I can solve for pH, because pH is the negative log of the H plus. So my pH in this case would be 5.1. Sig figs, these are all infinite sig figs because oh no, wait, this is one sig fig here. So 5.1 would work. I don't know if she taught you the pH sig fig rules. I'm assuming that she didn't, so I'm not going to hit you at all on sig figs with pH because I don't think that she taught you the log rule. So don't you fret about that. There you go to that person, I think. Or once again, if you have a question, you got to put it in like red on this document so that I can see it. Otherwise, I probably won't see it. Okay, redox. I didn't look at this question yet. I'm sorry to this person. I looked at most of them before I started this, but that was like at 2 this afternoon. Okay. Let me look at my equation. So we want to do cathode minus anode, or she taught you a different way, flipped it. My chlorine, my magnesium, I'm looking up on page 712 in my textbook to see what the redox potentials are. Negative 2.372. Chlorine, 1.358. Okay, so I can do this terribly. I'm sorry, it looks awful. I didn't put my screen down. Okay, so I looked at the magnesium and it's negative 2.372. And I looked at my chlorine and it is a positive 1.358. So my chlorine side happens to be my cathode and my magnesium side happens to be my anode. So when I do the E cell, I'm going to subtract my cathode one from my anode one. So that means my cathode is 1.358 minus my negative 2.372. So it should be a positive 3.730. So yes to that person. You're right. It should be a positive value. It would want to happen and could create a Voltaire cell. So you were correct. I was wrong. It should be a positive value. Thank you. Does it make a difference in this type of equation? Yes, it does. If it's a positive value, then you'll actually get electricity out of it. You will get 3.73 volts. It'll create a battery that has 3.73 volts. If it's a negative value, that means you actually have to put a battery to it. The battery has to be worth at least 3.73 volts to make that reaction happen. So as a positive value, it will produce electricity. As a negative value, you need to input that electricity to make it happen. So it does matter on the value. Okay. How do you get +3 for part D? Okay. So it is CrO42 minus. Okay, in this case, I am finding the oxidation number of the chromium. My oxygen here is worth a -2. Each oxygen is worth a -2, and there happens to be 4 total of them. So 2 times 4 is a -8. Now this whole compound has to be worth a -2 because the ion is worth a -2. So the only thing the chromium can be is a +6. I don't know how I got +3 because normally it would be a Cr2O4. No, it should be +6. If I had 2 chromates, then it would be +3, but that's not the case. +6. Thank you to that person. I really messed up this redox part. Other teachers would be like, just wanted to make sure you're checking. No, straight up, I just screwed it up. I'm sorry. I never do it just to see if you're checking. Okay. Number 4 in the review. Now I'm getting nervous about my redox. I did number 4. Oops. Okay, energy. Woo! Is chapter 15 energy? I think so. Okay. So, here we go. 5. Oops. All right. This is a woo-woo curve problem. So, woo. First thing you should do is make yourself a sloppy woo-woo curve and put in these 2 parts. Now I am dealing with water, which makes it kind of simple because this first flat part is where it's freezing. Freezing, melting happens at 0 degrees. The second flat part is where it's boiling. That happens at 100 degrees. And then I can look at the problem and tell myself, well, where am I and where do I want to go? The problem says I'm starting at ice at 0. Ice at 0 is right here because it's a solid on the left corner and a liquid on the right corner. And I want to get to steam at 165. Well, 165 is way up here. That's a 6. So this is where I want to get to. Here's my starting, and here's my ending. So I have to go over, and up. That's 4 steps. 1, 2, 3, 4. 4 steps. So let's start with number 1, Q1. Anytime you have a flat part, you're going to want to use the N delta H equation. And that's N delta H equation. Anytime you have a slant part, that's where you use MC delta T. C for slant, MC delta T, and the flat part is the other equation, N delta H. So here's my Q1. Q1 is equal to N delta H. My N stands for moles. I happen to have 78 grams of water. So I've got to get that into moles. So I've got to convert grams into moles. I use my periodic table and I find that 1 mole is 18.0148 grams of water. I got that 18.0148 by taking 2 hydrogens, 2 times 1.0079, plus my oxygen, 15.999. That's how I got my 18.0148. And I multiply that by the change in H. Here's where I got to go to the table that's on the worksheet. The change in H is the heat of something. So the heat of fusion in this case. Fusion is the liquid solid mix. 6.02 kilojoules per mole. Taking a look at my units, grams on top, grams on bottom, moles on top, moles on bottom, I'm left with kilojoules. So I'm going to bust things in my calculator as I go here. 78 times, oops. And times 6.02. So I'm left with 26.1 kilojoules. These problems of sig figs get crazy, so I'd really only care about 3 sig figs in the end. And I would tell you that in the problem if I did a problem like this. Okay, moving on to step 2, Q2. I'm in a slanty part. Here's my slanty part. C for slant, so I'm going to use MC delta T, where my M is my mass, 78 grams. C is the specific heat. Specific heat in this case of my liquid, because this middle spot is my liquid. Specific heat of water as a liquid is 4.184 joules per gram degree Celsius. And then change in T. Change in T is final minus initial. Now it's the final of this step to the initial of this step. The final of this step is 100, minus the initial of this step is 0. So the change in temperature is 100. 78 times 4.184 times 100. Looking at my units, grams on top, grams on bottom, Celsius on bottoms. This is Celsius on top, so I'm left with joules. Q2 equals 32635 joules. Now, joules isn't going to work in the end. I have to have everything in kilojoules, or you could have everything in joules, but I think kilojoules is easier. So I'm going to move it over 1, 2, 3, and I get 32.6 kilojoules. All right, moving on to the next part. This is Q3. Q3 is another flat part. Flat parts use N delta H. So my N, I have to get in the moles, 78 grams of water times 18.0148 on the bottom. That's how many grams there are in 1 mole of water. Same thing that I've got going up here. Times my heat of vaporization, 40.6 kilojoules per mole. Looking at my units, grams on top, grams on bottom, moles on top, moles on bottom, left with kilojoules. Q3. Oops, come on. I get 176 kilojoules. On to my last step, Q4. Q4 is this last little slanty part. Slant for MC delta T, C for slant. M is my 78 grams. C is my specific heat of my gas, 1.837 if I look at the table, times my change in temperature. And now that's only this part up here. I'm ending at 165, and that price starts at 100. It's not the whole temperature change, it's just of that segment. Or is 9313, and these ones are in joules because this 1.837 is in joules, which means if I move it over 1, 2, 3, I get 9.31 joules. At this point, I'm going to add up all of my parts, and I get my Q total is the addition of all those. So 26.1 plus 32.6 plus 176 plus 9.31. I got 244. Looks like on my answer key I got 243. I'm going to call myself a success. At this point, I mean, you're sig figging in different spots. It's okay. I call myself good. I may have pushed a button in the wrong spot. I wouldn't worry about it, and I'm just not going to. Because it's unlikely that I pushed a button. It's probably just sig figging differently. Okay. 11. Okay, we're on energy problem. Oh yeah. Okay, this problem is asking the specific heat capacity, so this is when we're dealing with Q equals MC delta T. My handwriting's getting sloppier. And I'm trying to find how much energy, or Q, is released. So Q equals M. In this case, my mass happens to be 5 grams. And my C is 24.4 joules per mole times degrees Celsius, times my T, which is change in temperature. My final is 30, from 50 to 30. My initial is 50. So now the question comes in is checking your units. I got Celsius on top, Celsius on bottom, grams on top, moles on bottom. That's where you might have been going wrong. I can't have grams and moles. I've got to have them equal. So I'm going to convert my grams into moles. 1 mole of, in this case, it's aluminum, according to the periodic table, is 26.982 grams. Grams at top, grams at bottom, moles on top, moles on bottom. I've now converted my aluminum mass into moles so that I can use the specific heat. Is specific heat normally in joules per mole? No, it's not. It's trying to be tricky, apparently. I didn't know I picked such a tricky one, but I did. So now I can boop, boop, boop in my calculator, and I happen to get 90. Ooh, that's a 9. 90 joules. The question, it'll be a negative 90 when you put it in your calculator, because 30 minus 50 is a negative 20. But the question is saying how much energy is released. Released is the negative value, so the amount of energy released, you'd say 90 joules is released. Or if you wanted to say my energy is negative 90. I'm saying the same kind of thing. Nuclear. The bad parts of fission and fusion. Okay. The bad parts of fission and fusion. The bad parts of fission would be, 1, you get nuclear waste, which is terrible. It sends out radioactive materials, which isn't good. We don't know where to store it, and it's a problem. 2, we are heating up the nearby lake water or anything that, or maybe ocean water that's by it. And if you heat up the water, then it decreases biodiversity. One reason would be there's less oxygen that can dissolve in there. And less oxygen inside your water, things don't live very well because fish breathe oxygen. 2, 3, uranium isn't really hard to find, but you do have to enrich it. You can't just use it in its natural state, so enriching it is pretty expensive. 4, did have 4, didn't I? Oh, nuclear meltdowns. You've got a chance that it could really lead to like Japan, so, or 3 Mile Island, or Chernobyl. All of our 3 big cases of nuclear fission gone bad. What is the bad part of fusion? The bad part of fusion is we have to make it super, super hot. It has to be so hot that you're basically containing the sun, which right now is really hard to do. We don't know how to do. I mean, we can do it with magnets or lasers, but the amount of energy that we put into it is more than the amount of energy we get out of it. So it's just not cost effective. Could you go over a nuclear reactor, how it works again, like all the parts and their jobs? 15. Yes, where do I have an image for that though? You need to see my screen. Where do I have an image for that? I know where I have an image for that. Ah. That's my little girl and my little boy. It's old now. I keep them a month old then. I hope they're still sleeping. They are. I can hear them. Okay. Go back out. Let's open this. I'm trying to get a picture of the reactor for you. Okay. Here's a nuclear reactor. Actually has a video. It's on your textbook website of how it works. But here's your how-to. So you got your uranium, which are what you need to do fission. That's a fissionable material. So uraniums are the black rods. The control rods are these reddish things that go in there. So when you want your reactor to work, you take out some of your control rods and you send in some neutrons. You send in a neutron and it breaks apart the uranium, gets absorbed by the uranium and breaks it apart. So now you've got fission happened. All the energy from the strong force is being released and in the form of heat. Now there's lots of neutrons, 3 neutrons that come out of every reaction, so we have to absorb some of those. That's what the control rods do. The control rods absorb the extra neutrons so the reaction doesn't go like crazy and basically explode the whole place. So yes, the uranium is going through fission. The control rods are soaking up the extra neutrons. The moderator, which is the yellow stuff, it will represent by the yellow stuff. It's basically all the stuff that the neutrons are flying through. It slows down the neutrons, so the neutrons just don't go screaming out. They have to slow down the neutrons so they get absorbed by the uranium, and then the uranium can split apart. So now the uranium has split in fission, and it produces a lot of energy. All that energy is in the form of heat, which actually makes steam from this water. The steam can go through the pipe and turn the turbine. A turbine is basically a big fan. And when a big fan turns, it's mechanical energy, and it can create electricity. A big fan turning, they usually use magnets to create electricity. That's a physics topic. But the electricity comes out. Electricity is what we use in the walls. Boom. That's the whole purpose of doing a nuclear reactor. But now their steam is in excess. We've used it a couple times, and we've got to cool it. So we're going to take a large source of water, pump in some water from that, cool down the steam, and pump out the hotter water. Yep, that's how it works. There you go. What is the difference between beta and electron capture? 1018. Beta is the release of an electron shooting out, and electron capture is capturing electrons. So a beta particle is when a neutron breaks in half. When a neutron breaks in half, it produces a proton, which stays inside the nucleus, and an electron, which shoots out of the nucleus. The beta particle is the electron that's shooting out of the nucleus. Electron capture is when an inner electron is actually absorbed by the nucleus. So it comes into the nucleus, hooks up with a proton to create a neutron. So they're kind of like the reverse of each other in a way. Why are some ionic compounds insoluble? Is this because they dissociate the cation and anion? Things are insoluble based on stuff we actually didn't really cover in class. It's based on entropy. And how detailed do I want to go with this? So basically this kind of topic, you don't really have to know the answer to this, but here's my gist of it. So when things dissolve, it's because you have the cation and the anion, they're hooked up together. Now they're really attracted to each other. And then you've got water molecules that swoop around it and pull it apart. Okay, now if you think about the energy that we have, I actually did go over this in class, but I told you never be questioned on it, and you won't. It's an AP topic. Okay, so you've got cation and anion. So there takes the amount of energy that holds these guys together. In order to separate them, you've got to give energy up. So they're holding on to each other. And what happens is the water really loves this cation and the water really loves this anion. So most things can separate because this love that water feels around the cation and the love of the anion is so much more than the love between here. There's so many more different molecules that are involved, and it creates this like little happy world where there's so much more love than this love together. So that's why they want to separate, because energy-wise it's more efficient. But sometimes it takes a lot of energy to make that happen. So sometimes you'll have this bond and this bond. These cations and anions are so much in love with each other that they don't want to separate. Even if you have all these water love going on, they're still like, nope, I like this guy better. I'm going to stick with him. That's kind of a simplistic way to talk about it. But it really comes down to the idea of enthalpy. Enthalpy is energy or heat. Enthalpy and heat are the exact same things, except for when you change pressure, which we don't in this class, so it doesn't matter. So enthalpy and heat is the same. So the amount of heat it takes to wrap around both of these and pull them apart doesn't make it energy efficient. And there are things where we have entropy. Entropy is the idea that the world wants to go to chaos. So you can imagine that this together is not as much chaos as these apart. And so when you add up the idea of enthalpy and of chaos, you come up to G, which is Gibbs free energy, which tells us about spontaneity, which is not something you need to cover in this. You don't cover in this class anymore. So why are some ionic compounds insoluble? Because of all that. And how much do you need to know? None of it, really. If I asked, well, I will ask you, some of you might have to talk about soluble versus insoluble in your theory part. I would really expect you to tell me, like, what happens when something is soluble. If something is insoluble, it just means that that part doesn't happen anymore. The idea of the water surrounding doesn't happen. I wouldn't say, why would one do it versus another? That's not part of it. It's just what happens when things are soluble that I expect you to write about. Oh my gosh, we're going to the last question. Oh. Are the only ions that are soluble the ones that are strong acids and bases, or do all ions dissociate? Strong acids and strong bases fully dissociate. Weak acids and weak bases partially dissociate. Anything that is considered soluble in the back of your periodic table is considered fully dissociated and would be soluble. Anything that is on your back of your periodic table called insoluble, then it partially dissociates, because everything dissociates a little bit based on KSP, just very, very little for some of them. How about salt hydrolysis? Salt hydrolysis is the idea that everything dissolves at least a little bit. So, yeah, I think I solved that wrong. Are only strong acids and bases dissociate? No. Ionic compounds can dissociate too. Acids and bases are part ionic, part molecular. They're both at the same time. Because sometimes the molecular characteristic, they stay together. Sometimes they have ionic, they kind of separate. So, woo! That was a lot. What time do we start this game? Ooh, I did that in like an hour. Even with computer malfunctions, that's amazing. You guys are amazing for sticking with it. I don't know how many viewers I've got, but I'm going to wait and see if you got any questions about the last things I talked about. I think I have like no viewers now. I totally understand. No, 2 viewers. One of them is me. Yes. I wouldn't have lasted this long either, so kudos to, oh, now I have 3. Nope, 2. Kudos to the other person who's with me today. You're probably just eating ice cream. That's cool. I don't have any ice cream. Why is that so blurry? That's awful. I know I talk too fast in these things, but is it too fast for you to get anything out of it? Somebody should let me know. I don't see anything in red. There's a lot of people on the Google Doc, though. 7 of you. Hey-o. All right, then I'm going to cut you off. To all of you, you will do lovely tomorrow. Have no fear. If the worksheet wasn't super hard, I think you're going to be just fine. It's not, like I said, if you take the hardest questions and the easiest questions, I'm not going to do these super hard ones. I'll do middle ones and easy ones. So that's how we roll. I'm closing my textbook. You should go to bed too. It's 10:30 and way past my bedtime. My little kids are getting up really early tomorrow. But they're still asleep, so that's good. Okay. Good night, all.